Question number 11. A block of mass capital M is attached with a 4 spring of force constant 2K, 2K, K and K. As shown, the block is capable of oscillating on a frictionless horizontal floor if it is displaced slightly and released. The frequency of resulting SHM would be: first option 1 by 2 pi root over 3K by M. Second option 1 by 2 pi root over 4K by M. Third option 1 by 2 pi root over 11K by 2M. And the fourth option 1 by 2 pi root over 2K by 3M. Now see the solution. So as per the given diagram, there are 4 springs are given. 2 of the spring have force constant 2K and 2K, and 2 of the other spring have force constant K, and the block are arranged like this. See, this is the one spring, this is another spring, force constant 2K and 2K, this is your third one, this is your fourth one, like this. So, and M is the block of mass M. So here these 2 springs can be said are in parallel, series. These 2 are in series and these 2 are in parallel. When the 2 springs are series, so they are written as 1 by K effective is equal to 1 by K1 plus 1 by K2. So we can convert this into this type of system. Here in place of 2 there is 1 spring, and this is your also another spring. So where 1 by K1 is equal to 1 by 2K plus 1 by 2K. So this is your K1 is equal to K, and K2 is equal to your K1, K2 is equal to your, these 2 are in parallel, the K plus K, which is your 2K. So now this is our just like a 2 spring, K1 force constant K, K2 force constant 2K, and now these 2 are in parallel. Suppose it is displaced x, so here force is your K1x, and from this force your K2x. So F restoring is your minus of K1x plus K2x, and K1 plus K2 is your 3Kx, that is your M into A. The A is your minus 3K by M into X, and this term your omega square. So omega square is your 3K by M. So omega is root over. So frequency F is your 1 by 2 pi root over 3K by M. This is the frequency. So our correct option, your option number 1 is the correct option. So answer 1 is the correct answer. Question number 12. A simple pendulum is suspended from the roof of a trolley that moves freely down an inclined plane of inclination alpha. With the horizontal, the time period of oscillation of the pendulum is: the first option 2 pi root over L by G, second option 2 pi root over L by G cos alpha, third option 2 pi root over L by G sin alpha, and the fourth option 2 pi root over L by G tan alpha. See, as per the given, this is the inclined plane having inclination alpha, and here a trolley is given. So this trolley have acceleration g sin alpha in this direction. Now, with respect to the trolley, this is the actually pendulum. With respect to trolley, if we are making FBD here, the one force is on this your mg, another force here in this direction, and that force is your pseudo force mg sin alpha. So now with these two forces, the string have some angle. So this give us the resultant like this. So this is the vertical line. So now our string will be somewhere like this. So downward force here your mg, and in this along the plane is your pseudo force here mg sin alpha. This is the equilibrium condition and T is the tension here. Now the resultant force T will be resultant of this T. For equilibrium, T square must be equal to your resultant of these two. So see, this angle your alpha, so this angle will be your 90 plus alpha. The resultant of these two is your mg square plus mg sin alpha whole square plus 2mg into mg sin alpha and cos 90 plus alpha, and simplify. Mg square we can take common, 1 plus sin square alpha, and this will be your minus 2 sin square alpha. So this become your 1 minus sin square alpha, that is your cos square alpha. So mg cos alpha, this is the T. So resultant here force is mg cos alpha. So time period is equal to your 2 pi root over L by G effective. Here G effective your G cos alpha. So 2 pi root over L by G cos alpha. So this mg cos alpha can be written as m into G effective. So the time period relation will be a 2 pi root over L by under root G cos alpha. So our correct option, your option number 2 is the correct answer. Now question number 13. Question is given as a weakly damped harmonic oscillator of frequency N1 is driven by an external periodic force of frequency N2. When the steady state is reached, the frequency of the oscillator is equal to first option N1, second option N2, third option N1 plus N2 by 2, and the fourth option your root over N1 plus N2. See, in case of force oscillation, the force oscillation itself, it is clear that when a body is forced to oscillate because of certain forces, in force oscillation, at equilibrium, the oscillation frequency will be the same as the frequency of the force has been applied. So at equilibrium or at steady state, oscillation frequency of oscillator, oscillation frequency of oscillator must be equal to frequency of periodic force, must be equal to frequency of periodic force, which is N2. So hence correct answer your option number 2. So answer 2 is the correct answer. Question number 14. Springs of force constant K2, K4, K8, K and so on up to 2048 K are connected in series. A mass M is attached to force one end of the series and the system is allowed to oscillate. The time period of oscillation is approximately. First option 2 pi root over m by 2k. Second option 2 pi by k. Third option 2 pi root over m by 4k. And the fourth option 2 pi root over 4m by k. Here, as per the question here, number of springs are given 1, 2, 3 and so on, and their time constant vary as k, 2k, 4k and this is your 2048 k. So all these are in series. So this can be written with a one spring of force constant K effective. So 1 by K effective is equal to your 1 by K1 plus 1 by K2 and so on. So 1 by K plus 1 by K1 means 2K, 1 by 4K like this. So further we can say 1 plus 1 by 2 plus 1 by 4. So here springs are given having force constant K, 2K, 4K like that up to infinity. From that a mass M is suspended. So this all are taken as just like in series. So in place of all this we can represent with one spring of force constant called K effective. 1 by K effective or 1 by K1 plus 1 by K2 and so on. So 1 by K plus 1 by 2K plus 1 by 4K, and this is now infinite series. So summation of the sum of the infinite series your A by 1 minus R, the 1 by 1 minus 1 by 2. So this will be your 2 by K. So from here we can get K effective is your K by 2. Now, so this is just like a one spring of force constant K by 2. Now time period T is 2 pi under root m by K effective, and K effective is your K by 2. So our answer will be your 2 pi under root 2 m by K. So this is our answer time period. So option number 2 is the correct answer. Now see question number 15. The progressive wave equation in the differential form is given as, first option is your 1 by omega square d2y by dt square is equal to 1 by k square d2y by dx square. In the second option 1 by omega square is your dy by dt is equal to minus 1 by k dy by dx. Third option 1 by omega square d2y by dt square is equal to 1 by k square d2y by dx square. And the fourth option 1 by omega dy by dt is equal to 1 by k dy by dx. See, progressive wave equation. Progressive wave equation written as y is equal to a sine omega t minus kx or kx minus omega t. See, dy by dt we can say a omega cos omega t minus kx, and d2y by dt square is minus a omega square sin omega t minus kx. Similarly, dv by dx written as minus a k cos omega t minus kx, and d2y by dx square is ka square, and cos omega t further become your minus sin omega t minus kx. Now see from first and second. Let this is your equation number 1, this is your equation number 2. So d2y by dt square from first and second is equal to a sin omega t minus kx minus a sin omega t minus kx written as d2y by dx square by k square. So this is nothing 1 by omega square d2y by dt square is equal to 1 by k square d2y by dx square. So this is the relation of progressive wave equation. So option number 1 is the correct answer. So answer 1 is the correct answer. Question number 16. A cylindrical log of wood is floating in a large pool of water with its length normal to the water surface. The log has a radius r, mass m, length l and density rho. If the log is depressed below its equilibrium depth d but not up to the beneath the surface of water and then release, it execute harmonic motion with a time period t. Assume density of water is to be rho, the value of time period. First option given t is equal to 2 pi root over m by 2 rho r L g. Second option t is equal to 2 pi by r root over m by rho r g. Third option t is equal to your m by 2 pi r l. Fourth option t is equal to root over m by pi r square into l. See the solution. It is given a log, right now it is floating on a water. So when it is floating on a water, at this moment let y naught length is inside the water. Total length of this your r. So in equilibrium mg is equal to, at equilibrium weight of the cylinder is equal to your buoyancy force. Buoyancy force your pi r square y naught, density of water your rho into g. So y naught is nothing g by pi r square rho into g, and g cancel. Y naught mg by pi r square rho g, g and g we can cancel, m by pi r square into rho. This is initially. Now slightly it is depressed. Let it is depressed slightly by y. So buoyancy force, restoring force is equal to your minus of buoyancy force minus weight. Now buoyancy force will be more slightly the pi r square y plus y naught rho g minus mg. See, pi r square y naught rho g, pi r square y naught rho g, that is equal to mg, minus pi r square rho g into y. This is equal to m into a, acceleration. So a is equal to your minus pi r square rho g by m into y, and this is your omega square. So this is your a is your minus omega square y, time period t is 2 pi by omega, and which is your 2 pi, and omega is this. So this is your m by pi r square rho into g. This is the time period. So now we can check from here. 2 pi, this r square we can take outside. So 2 pi r root over m by pi rho g. So our correct option is your option number 2. Option number 2 is the correct option. The question number 17. A particle is vibrating in SHM. Its velocity are v1 and v2 when the displacement from the mean position are y1 and y2. The time period of oscillation of the particle is given as first option 2 pi root over y1 square plus y2 square by v1 square plus v2 square. Second option 2 pi root over v1 square plus v2 square by y1 square plus y2 square. Third option 2 pi root over v2 square plus v1 square by y1 square plus y2 square. And the fourth option 2 pi root over y1 square minus y2 square by v2 square plus v1 square. See, as we know, velocity of the particle is given as v square, or v is equal to omega root over a minus a square minus y square. It is given as when the displacement is your y1, then the velocity your v1. When displacement is your y2, then the velocity your v2. So v1 square is equal to omega square a square minus y1 square. v2 square is equal to your omega square a square minus y2 square. See, from first and second, from equation 1 and 2, v2 square is equal to your omega square a square can be written as v1 square plus v1 square plus omega square y1 square minus omega square y2 square. So omega square is equal to your v2 square minus v1 square by y1 square minus y2 square. So time period, they are asking the time period of oscillation. So time period is your 2 pi by omega. So which is your 2 pi, and omega is your y1 square minus y2 square by v2 square minus v1 square. This is the option. So option number 4 is the correct answer. Question number 18. The two bodies A and B of equal masses are suspended from two separate massless springs of force constant K1 and K2 respectively. If the two oscillates vertically such that their maximum velocities are equal, the ratio of the amplitude of A to that of B is first option K1 by K2, second option K2 by K1, third option root over K1 by K2, The fourth option root over K2 by K1. So as per the given information, it is given as two bodies A and B of equal mass have their maximum velocities are equal. When the body is performing simple harmonic motion, so maximum velocity of the particle is at their mean position, which is given as A omega. So for one, A1 omega 1 is equal to your A2 omega 2. So A1 omega for one spring your 2 pi or root over omega for in case of spring mass system. As we know, T is your 2 pi under root m by k. So 2 pi by T is your omega, which is your k by m, we can say. So omega 1 is written as k1 and mass is same, the k1 by m. And for second, A2 K2 by m. So this gives us A1 by A2 is equal to root over K2 by K1. So option number 4 is the correct option. Question number 19. A body hung from a vertical spring execute vertical oscillation with a time period t. The body is now immersed in a non-viscous liquid having density 1/10 of that of the body. When set into vertical oscillation with the body remaining fully immersed in the liquid all the time period will become. First is your root over under root 10 by 9 into t. Second option root over 9 by 10 into t. Third option t. And the fourth option t by 10. Now, in case of spring mass system, time period is given as 2 pi under root m by k. Now, if the body is your immersed in a liquid and it remain inside a liquid forever, so what will be the difference? Difference will be there. When mg is acting up downward, buoyancy force will be upward. Since the body will remain inside a liquid, the buoyancy force will be always your constant. So now the elongation on the spring will be less, but there is no change in the restoring force, because whatever the buoyancy force and mg, that will be your constant. So in that case also time period t dash will remain equal to your t. So the correct option your option number 3. Question number 20. A body of mass m is suspended from two light springs of force constant k1 and k2 respectively. The period of vertical oscillation are t1 and t2. Now the same body is suspended from the same two springs with are first connected in series and then in parallel. The period of vertical oscillations are Ts and Tp respectively. So first option is that Tp is less than T1, less than T2 and less than Ts, and K1 is greater than K2. Second option, 1 by Tp square is equal to 1 by T1 square plus 1 by T2 square. Third option, Ts square is equal to your T1 square plus T2 square. And the fourth option, all of these. Now check how to do. See, in the first case they are saying when the mass is suspended from a spring of force constant K1, then T1 is 2 pi root over m by K1. So this we can write T1 square is equal to your 4 pi square m by K1. Similarly, in the second case, when the spring have force constant K2 and mass m, in the same way T2 square will be your 4 pi square m by K2. Now these two are in series and parallel. When series like this, K1, K2, and this is the mass. Then time period. So first K effective. K effective is your K1, K2 by K1 plus K2. So Ts square is equal to 4 pi square m by K effective, which is 4 pi square m. K effective is your K1 plus K2 by K1 into K2. Now this we can say 4 pi square m K1 plus K2. K1 is nothing, we can check from here, 4 pi square m. K1 is this by T1 square, 1 by T1 square plus 1 by T2 square by K1 into K2, 4 pi square m. K1 K2 means 4 pi square m by 1 by T1 square into 1 by T2 square. So this is nothing, this and this cancel, T1 square plus T2 square. So Ts square is equal to your T1 square plus T2 square, that we can say Ts square. And now when these are in parallel, parallel means like this, K1, K2, then time period Tp, then this is your effective, K effective will be your K1 plus K2. So Tp square is equal to your 4 pi square m by K effective in K1 plus K2. So Tp square is your 4 pi square m, and K1 plus K2 we can put from here. So that is your 4 pi square m 1 by T1 plus 1 by T2. So this is nothing, 1 by T1 plus 1 by T2 is equal to your 1 by T P square. Now see from here T1 square and this is your T2 square. So when the series, this is the one option correct, another option your this is also correct. So option number 2 and 3 correct. And regarding time period, see if K1 is your less, if K1 is less, so T1 will be your more, and when K2 is your less, T2 will be your more. So now from here we can get the first option is also correct. So the correct answer is your answer number 4. All of the given answer are correct option.